Hi, I'm Ted Palmer, an environmental scientist here at the Environmental Protection Agency. Today in this module, we're going to look at environmental fate and transport. Now, if you remember our paradigm when we showed the whole scoping document, in the upper left corner, we've already talked about source characterization. Now, what happens once that source is released into the atmosphere? How's it going to get transported from point A to point B? How's it going to get to the person that's going to breathe it in? That's what we call environmental fate and transport. And in this module, we'll look at just that. So fate and transport is the process of understanding how a pollutant moves through or changed in the environment. For air toxics, we're mainly going to be concerned with the air pathway and how that air toxic is transported via the air pathway to our subject or our receptor, as we had mentioned earlier. Now, if you remember our diagram here, where we had a complete picture, if you look in the upper left corner, we had talked about sources, and Ann Pope's module talked about the sources being emitted from major area and mobile sources. Well, now we're going to talk about how that source moves in the atmosphere. So how does it move? Well, to many of us, the atmospheric motion and how meteorology transports air pollution is a big, giant black box. Let's try to look into that black box and get a little bit of a clue as to what's going on. We're going to break it down simply for you into four major components that make up fate and transport in the air. First is source characterization, and we'll talk about what part of the source and what type of emissions will affect how a pollutant is transported. Second, we'll talk about meteorology, something everyone's familiar with, the weather every day. How does that affect fate and transport? And finally, we'll talk about physical factors in chemistry and how those weigh into fate and transport. So let's start with source characteristics. Probably the most important characteristic from an emission perspective is the emission rate, how much of the pollutant or that air toxic is actually being emitted. If you double the emissions, guess what? You'll double the concentration that's available for someone when they breathe it. If you triple it, you'll triple it. You got the idea. A second factor that's important in source characterization is the plume itself, the characteristics of how that pollutant comes out of the stack. Is it coming out hot? Is it coming out cold? Is it coming out with a large exit velocity? Is it coming out fast or slow? Those factors will weigh into how that plume actually gets dispersed. And we call the final portion of this plume height. So the plume height is actually made up of two components. The physical stack height, so how big the stack is released. When it's released from the ground, that's a ground level source. The stack would be 0. When it's a 10-meter stack, we would call our stack 10 meters. And the second factor, which is a little more complicated, is what we call plume rise. How that plume will rise in the atmosphere and how high that plume will actually go. And that's a function of several things. How fast it's coming out, or an exit velocity, how hot the plume is. Think of a hot air balloon. The more hot air you put into that balloon, the higher the balloon will rise. Same thing with a plume. And finally, it's a function of the wind speed. The faster the wind, the quicker the plume will get bent over and the lower the plume height will be. The slower the wind, the more chance it has to rise. Our next factor is meteorology. There's a number of important meteorological factors that affect fate and transport. Winds, and we'll talk about that. Atmospheric stability, and I'll explain that in a second. And finally, precipitation. So how do winds play into it? Well, we just talked about our plume rise, and they're very important in that. But one of the most important things is, what direction is the wind blowing? If the wind's not blowing from you or towards you from your pollutant source, you're probably not going to be affected by it. And we talked about speed. The lighter the wind speeds are, the higher that plume rise can grow, because it has much more chance to be buoyant. When the wind is high, that plume gets bent over much quickly. And we'll show you a couple figures in a little while that spell this out for us and show us visually actually how this happens in the real world. And wind direction, like I mentioned. If you're not downwind from the way the wind is blowing, you're not going to feel the source. One of the things meteorologists use to see how wind blows in different wind directions is a windrose. In this example, you can see the windrows shows, and these are little barbs or lines that draw out from the center that show the direction that the wind flows. Basically, in this example I'm showing here, the wind is blowing from the north to south a majority of the year. And you can also tell on the windrows how fast the wind is blowing. So the wider those little barbs are, the faster the wind is blowing. Another concept that's very important in freight and transport is atmospheric turbulence. Think of turbulence as how active the atmosphere is. The more turbulence we have, the more chance the plume will get to grow. Now, when that plume is released into the atmosphere, it's only growing, like we said, because of the buoyancy of the plume, and the wind may be moving it very slowly. But how does the plume, if you notice in the real world, a plume will grow. And as it goes downwind further and further, that plume gets wider and wider. What's happening is, on the edges of that plume, clean air is actually getting entrained or brought into the plume itself. So the plume has a chance to grow as it goes further and further downwind. The more turbulent it is, the quicker that plume grows. But keep in mind, the quicker that plume grows, the lower and lower the concentration becomes as you go downwind, because you're actually diluting the plume with fresh air as it moves further down. Another concept is precipitation. Now, if the plume comes in contact with a cloud or rain or sleet or snow, the droplets can actually wash or scavenge out the plume itself. And then the plume will fall to the ground in the form of liquid or water droplets that contain the air toxic we were dealing with previously in the air. Another important factor in freight and transport are physical factors. Think of the pollutant itself. Some pollutants are in gaseous form, others are in particulate or particle form. And depending on the size of these particles, they could settle out to the ground very, very quickly. Others can stay suspended in the world for many, many years. So depending on the physical properties of the air toxic itself, that plume may or may not settle out quickly. Another is a physical structure can get in the way of the plume itself, such as a building. Those of you who live up in the north know that it always happens, no matter where you park your car, you get the steepest snowdrift right behind your car. Well, what's happening is the wind that's flying over your house is generally creating what we call a downwash region, or an area that's kind of dead air, where the wind really cannot flow in a laminar fashion. And in this area, the pollutant could settle very, very, very quickly and get to the ground very quickly. So you could have some very high ambient concentrations in downwash areas. So it's something that has to be considered when we look at plumes. Same thing can happen with a mountain, downwind from a mountain. Upwind, you might have very strong winds, and downwind, you might have very light winds. So we have to look at other factors, such as these physical factors, when we look at plumes. And a final thing in freight and transport that we look at is the chemistry of the plume itself. While most pollutants that we look at from an air toxic perspective, we treat them as pretty much inert type pollutants. In other words, we don't allow them to react in the short run. Some of them are very reactive, such as formaldehyde. When you introduce sunlight and photochemistry starts to begin, the pollutant can actually change forms into other pollutants that sometimes are more toxic than the original pollutant. So chemistry must be considered for certain pollutants. So what does all this mean to freight and transport? And if we take a plume as it's coming out of the stack, it's coming out at a certain mass and a certain concentration. The closer you are, the closer you are to that stack, the smaller that plume is. I mentioned this earlier. Think of taking a slice through that plume. And that slice is going to have a certain amount of mass in it. And as the plume goes further and further downwind, as that plume grows, that slice will become larger and larger. And if you have the same amount of mass, and that slice is larger, you're going to reduce the concentration. So close to the stack, the concentration's high. As you get further and further downwind, that concentration actually decreases with distance. Let's look at a couple examples of some plumes in the real world. This one I have right here is an elevated stack. And you'll notice how the plume rise is growing. It goes straight up out of the stack, and it's going up into high levels of the atmosphere. And this plume actually never even touches the ground. This would tell me right away this is very, very light winds and probably very stable atmospheric conditions or stable turbulence conditions. We measure turbulence with three different kind of factors: stable, neutral, where you don't have much mixing whatsoever, or unstable. Think of unstable as a day like when you have billowing cumulus clouds in the sky. As in our next example here, you'll notice our plume now is elevated much higher. And I would suspect in this one we have unstable conditions and much higher winds. And you could notice that the plume is not only bending over much quickly, but it's also coming to the ground much quicker. These types of conditions can lead to much higher ground level concentrations. And keep in mind, most of us are on the ground, so how and when that plume hits the ground is very important to determine the ambient concentration that's available when somebody has to breathe this air toxic in. Probably a source that's most persistent and can cause some very high-level ground concentrations is a very low-level source. How many of you have gone to a campfire, and no matter where you sit around that campfire, that smoke's always in your face? I know it happens to me all the time. And it's not unique. It happens to a lot of people. That's because on a ground level source, and especially under light winds, that plume will tend to meander around and just go from place to place. There's very little wind to move it, so it's dispersing at a very slow rate, and no matter where you sit, you always appear to be downwind from the plume. So let's look at an example of what a plume looks like in the real world. Now, we use, as air quality scientists here at EPA, we use a series of atmospheric dispersion models. Now, here's a model that we've developed, or actually a professor at Penn State developed, Alfred Blackadaw, developed this many, many years ago to simulate what a plume would look like in the real world if you could actually see the plume. In this example, we had unstable atmosphere, so the atmosphere was conducive to mixing. We had a lot of turbulence going on. And in this one, we had high wind speeds, so the plume went downwind very, very quickly. And you'll notice there's two different views in this model. The upper half of the model showing a view looking directly down on the plume. And the second, or the bottom half, is showing a side view of the plume itself. You notice this is an elevated plume. And at very, very close to the stack, the plume's not even touching the ground. So if you were at just below that plume, you'd probably be in air relatively clean. But as you went further down, you'll notice how the plume hits the ground, probably 2 or 3 stack heights downwind, and the concentration peaks down there. You'll notice that this plume is well dispersed and moves quickly downwind. So we have an unstable conditions and strong wind speeds. What happens if we take our elevated plume and bring it to the ground? You'll notice that clean area that I talked about previously is no longer present. This ground level source, or our campfire that we just talked about, is right there. So very, very quickly, and at a much higher concentration, that plume is brought to the ground. If you remember our example earlier where I showed you how we sliced the plume, well, the bigger you can make that slice, the less the concentration is. If the plume comes to the ground very, very quickly, that slice is going to be very narrow. We're going to have a much higher concentration. In our next example, let's elevate the stack back up now and change the stability, or the turbulence. Where our previous two were unstable, this one will make it stable conditions. We'll make the atmosphere less conducive to mixing. And we'll raise the wind speed up to 10 meters per second again. Notice now that this plume is much narrower. You don't get the mixing that we showed in the previous example. And if you look at the bottom slide, when you look at the side view of the plume itself, you can see it's very, very narrow. The plume doesn't even touch the ground at all. So these are some quick examples as how turbulence and wind speed affect the plume in the real world. So what's all this mean? How do we predict it? As I mentioned, we use air quality models, or numerical models that simulate what's going on in the real world. Models are a great friend to risk assessment and fate transport. They can predict both acute or short-term impacts, as well as chronic or long-term impacts. A model, typical model, can simulate a year in a matter of minutes. Another feature of a model is we can model many, many different points out there. So we can model the fence line of a facility, we can model a neighborhood, we can model many neighborhoods. Some of our modeling exercises actually model the entire country. Another thing about modeling is you could try different things. You could double the emissions, you could double the size of the stack. You could do what we call what-ifs, to see what it would take and what's the final effect on ground level concentration. Keep in mind that is the ultimate goal of our analysis, is to come up with that concentration in ambient air that's available for somebody to breathe. So if you want to learn more about dispersion models or atmospheric models, probably your best source is to go to our SCRAM, or Support Center for Regulatory Atmospheric Models website. There's the URL. You can click in there, and you can get all sorts of model guidelines and guidance, which models are preferred by EPA, just by going to this website. Now, if you looked on SCRAM, you'll find many, many air quality models. Probably some of the most prevalent, and the ones we use most, is the AirMod model, which is the workhorse. It's a regulatory model, so it's preferred by the EPA for many types of air quality analysis. And it'll simulate anything from 1 hour to a whole year. Our HEM model, which we'll show you in a little while, we'll show you an example of that in a demonstration, actually uses the AirMod model in itself to predict ambient concentrations downwind. Another model that we use is called CalPuff, that simulates puffs of air as it goes through the atmosphere. And finally, the CMAC model. I talked about chemistry being a potential to determine what's going on in the ambient air. Well, the CMAC model is very good at chemistry. So each one of these models has plus and minuses about it. The AirMod by far is the biggest workhorse and probably the easiest of those three to run. Another thing that's unique to modeling is we use different terms. Modelers are unique people. When we refer to a point source in modeling, we generally mean we know the location of it. So we would generally refer to a stack as a point source. We can generally measure where that stack is, and as we mentioned earlier, the height of that stack. So we'll know all about the physical characteristics of the stack itself. We call these point sources. When we really don't know exactly where the pollutant's coming from, say for instance coming from leaks at an oil refinery that come from pumps and flanges and all sorts of equipment around the facility itself. We call these fugitive emissions. A wastewater pond where you have air toxics off-gassing from the pond could be an example of a fugitive release. Now these fugitive releases are represented slightly different in an air quality model. We don't, once again, have a stack to put the fugitive release at. So we call them area sources. I know the Clean Air Act has its own definition of area sources, but modelers do as well. And from a modeling perspective, an area source is simply a two-dimensional surface in which contains the emissions that we're concerned with. If we want to add a third dimension to that area source, we'll call it a volume source. And finally, our last type of source that modelers look at are line sources. A road is a perfect example of a line source. It doesn't really have a width, but it sure has a length to it. So that would be a line source. A second way that we could predict fate in transport is through ambient monitoring. So we talked about modeling, being able to predict very quickly what a one-year concentration might be in the atmosphere. If we're out there doing ambient monitoring, it would take us a whole year to go out and measure that same concentration. But there are plus and minuses, and we'll talk about that in a few seconds, in both approaches. Generally, ambient monitoring is used in enforcement cases. If you want to go out and see what's really going on in the real world, models are great, but the proof is actually going out there and measuring what you think you're going to predict. Another is we actually use ambient monitoring to validate our models, so we know how well our models are performing in the real world. Another important consideration for ambient monitoring is if we just don't have emission rates for a particular stack? Now, we talked about emissions earlier, but what happens if you don't know how much of a certain air toxic is coming out of that stack? Well, like I mentioned, you don't know the physical parameters of that stack, the height, this flow. You can go out and measure with an ambient monitor, and you don't need that. So you want to find out more about air toxic monitoring? A good resource is to go to the EPA website. If you want historical data that we've measured for air toxics as well as other pollutants, go to the Air Data website, and you can see the URL on our screen. If you want a little bit more about monitoring itself and techniques, what methods are out there, how to actually set up a monitor, go to our AMTech, or Atmospheric Modeling Technology and Information Center website. And there's a wealth of knowledge out there on that. We're going to spend the next couple minutes with one of our air toxic monitoring experts, Dr. David Shiloh, showing us just what an air toxic monitor looks like and how it works in the real world. David?
Thanks, Ted, and welcome to the monitoring station. In here we have a variety of different air monitoring equipment for collecting air samples. Today I'm going to talk to you about a VOC canister sampler that is capable of collecting up to 16 canisters through a 24-hour period. Here we have one 6-liter Suma canister connected to this sampler to collect an air sample. This 6-liter canister is under vacuum, so there's no air inside. What we do is we will open up the valve and allow this sampler to pump the canister full of an air sample that is a representation of the ambient air outside. So why don't we go ahead and begin collecting an air sample. What I do is I open up the valve, and now the canister sampler is beginning to fill this canister with an air sample. We will let this go for 24 hours, and then we'll come back tomorrow and close the valve and take the canister to the analytical laboratory. Okay, now that we've collected our 24-hour air sample, the next step is to bring it to the analytical laboratory. And here's an example where we have now a week's worth of 24-hour canisters that have been collected, and we now need to do the analysis of that air inside that canister. Again, a representation of the ambient air outside. We bring that into the lab and we hook them up to an auto sampler that we can take a portion of that air and run it through our analytical system. Our analytical system in this particular situation is a GC mass spec, a gas chromatography mass selective detector. We start out by pre-concentrating an aliquot of the air sample out of each canister, and then we run it through the GCMS. When the analysis is completed, we will have an end result of a chromatogram showing all the VOCs inside that particular air sample. Okay, here we have the final analysis of the chromatogram of the canister that we have collected over the last 24 hours. You can see here it looks like we did find a few VOCs in our sample. The component maybe around 11 minutes looks like it might be benzene, and we'll look at the final concentration of that, but from what it looks like it could be anywhere from 3 to 5 micrograms per cubic meter. But once we get our data analysis report, we'll know the exact concentrations of each VOC in our sample.
Thanks, David. That was great. So which one do I use? Model, monitor. They both look good. Well, let's look at the plus and minuses of each. Modeling, pretty quick. Like I said, get a whole year's worth of ambient concentrations in an hour. It's also relatively inexpensive. They don't pay modelers a lot of money, by the way. You could look at results over a much larger spatial domain than you could a monitor. If you wanted 10 locations, just plug 10 different receptors in your model. If you wanted 100, you could plug in 100. If you wanted to do that with monitoring, you'd need 100 monitors to do that. Problem is, there's a degree of uncertainty with that prediction. These are models. We're trying to simulate a very complex phenomenon that's going on in the atmosphere. There's a lot of uncertainty in the emissions themselves. We talked about the chemistry, or how that plume actually travels from point A to point B. So keep in mind, while it might be inexpensive and give you a lot of information very quickly, there's a degree of uncertainty with air quality modeling. Ambient monitoring, on the other hand, much less uncertainty in most cases. Problem is, it's time consuming. To get 6 months worth of data, you need 6 months at least. There are limits to some of the methods that we look at. There are logistic issues. What happens if you place your monitor out in the field, you come back the next day, and somebody decides to do some target practice on your monitor? Or is electricity available to run your monitor? These are things that need to be considered when you place a monitor out there. It's also expensive. You have lab costs and equipment costs. And once again, like I mentioned earlier, if you wanted multiple locations from your monitor, you'll need multiple monitors to do that with, unlike the model where you could just put in different receptors. So it gets us back to the question I asked, which one do you use, a model or a monitor? Well, in general, in our risk assessments, we like to use both. Modeling is the primary tool we use for fate and transport, and as we'll show you in our HEM demonstration, we can very quickly use it to predict what we see our ambient concentrations in the air and eventually for exposure and risk calculations. When we use a monitor in conjunction with a model, it gives us a great degree of confidence in our results. So it's always nice to go out and place a monitor to see how well our model is actually doing and validate the model itself. So now we've learned a little bit about fate and transport and how the pollutant gets from point A to point B and how we predict an ambient concentration to use for our risk assessment.